Would someone like to get us started off with a problem you'd like to go over?
Could we go over the problem 8, the 2020 midterm part 1-2?
Absolutely. That's a fun one. Okay, so treatment of NN-diethylbenzylamine with methyl iodide yields the pure product shown in the 600 megahertz NMR spectrum and chloroform below. In the full spectrum, integrals are shown on top. In the expansions, the peak positions are shown on top in ppm, and the integrals are next. And then we have a peak printout if we want to calculate coupling constants. So if I remember correctly, the first question is asking, what is the chemical equation for the reaction? So effectively, what molecule are we making? Would anyone like to answer that?
Ammonium salt.
Yes. And what are the substituents on the ammonium salt?
There's one methyl group, 2 ethyl group, and then benzyl group.
Right. So in the jam session, I opened up Pymol and I modeled that molecule, but basically it's a tetrahedral ammonium. It's an ammonium salt. It's got 4 substituents, so it's forced to have a positive charge. That's what the iodine counterion is for. And it's not chiral. It has 2 ethyl groups, a methyl group, and a benzyl group. So why then do the multiplets at 3.45 and 3.52 appear the way that we do? So the first thing that might be useful is to explain what the phenomenon is that's going on. Why do we observe what we do?
Is it coupling to the nitrogen now? That is positive or something? I read something about that being maybe possible.
So the NMR active nitrogen nuclei is N, maybe James can spot me. Which one is
N15? So N15 has a nuclear dipole. So N15 does what you could call normal coupling. N14, but that's only 0.37%, 0.38% of the natural abundance. So that's not, 99.6% of your molecules are N14. And while N14 does have a nuclear quadrupole, in all but very special circumstances, you do not see coupling effects of the nuclear quadrupole. The only case you see a substantial effect is in the case of a tetrasymmetrical ammonium ion like ammonium chloride. So ammonium chloride in DMSO, you see a triplet, but like chloroform, but with a very big J value. But that's exceptional, like the CDCl3 peak in the C13 NMR. But that's exceptional. In some cases, you get a slight quadrupolar broadening. Silverstein talks about this for hydrogens that are essentially next to the nitrogen. But that's only a little broadening, and that's not what we're seeing over here. So so the short answer is it's nothing per se to do with the nitrogen.
I had forgotten about that phenomenon. So thank you, Brian, for reminding us. If it's not coupling to the nitrogen, that means we're only observing proton-proton couplings. Why then do there appear to be 2 signals for 4 protons? And just to clarify, we're speaking about the 2 methylenes of the 2 ethyl groups. So if you haven't yet, it might be useful to, I have my document camera, I can sketch out what I'm talking about.
So if I remember correctly, it was somehow the case that those methylene protons were apparent diastereotopic protons. And so they gave rise to a coupling to each other, which was a doublet. And then each one is coupling their adjacent methyl protons, which was a quartet. So what we're seeing are two overlapping doublet of quartet peaks
Yes. And
for the
I'll ask you-
methylene protons.
I'll ask you one follow-up question. Can you explain why a doublet of, and we'll go back and explain the other parts, but I also want to ask Chris, can you explain why a doublet of quartets appears as only 6 signals? And can you also explain why they don't appear to be in integer numbers of height? It doesn't look like Pascal's triangle.
Yes, but only with the aid of the magic Excel spreadsheet where I can punch the coupling constants. Yes, exactly.
So what coupling constants are we looking for? Remember that we're trying to replicate a doublet of quartets. So we need 1 large coupling and 3 small couplings.
Okay, what do I have? 14.4 and 7.3. I think, no, wait. Partho, Franco, someone help me out. Are those numbers what? Are those? 14.4 and 7.3. Yeah, okay.
Yeah, sorry, I was muted. Those are the correct values, but this appears to be a 1 to 3 to 4 to 4 to 3 to 1 pattern. Why does this not, let me zoom in. This doesn't appear to be 1 to 3 to 4, 1, 3, 4, 4, 3, 1.
It had something to do with the fact that the large coupling is essentially exactly double the small coupling, which is going to give rise to 2 peaks somewhere in there overlapping each other. Or more than 2 peaks in there overlapping each other.
So that's the answer to the first question. The reason that a doublet of quartets would appear as only 6 signals rather than 8. So if you think in the extreme case, a doublet of quartets would just be 2 quartets that are well separated from one another. Because 14.4 is on the order of twice 7.3, you can mess around with this number on your own time with this spreadsheet, but you can see that if one coupling constant is a multiple of another, you end up with coincident peaks, and their relative abundances or relative heights will start to overlap with one another and lead to interesting patterns like 1, 3, 4, 4, 3, 1. So now that we've answered that question, why do these sets of peaks not appear to be the same pattern? There are some peaks that are taller than others where we would expect them to be equal. Why is that?
Is it because they're coupled together and so they're leaning?
Yes. So these protons in particular would be in an AB pattern. They are chemically inequivalent, but they are close enough together in chemical shift that we observe what's called tenting into one another. So if they were 2 doublets, it would be a simpler case, but because it's a larger multiplet, some of these peaks are, well, I won't say they're affected more than other ones, but you can see that in general, the trend seems to be that for the left pattern, the peaks on the right are taller. For the right pattern, the peaks on the left are taller. Maybe now we can talk about what are these 2, sorry, I was trying to zoom out. What are these 2 protons and why do we observe 2 patterns for them? So again, these are the methylenes on each of the 2 ethyl groups of our product. Can someone explain the coupling?
One geminal and one vicinal coupling. So it's because they're inequivalent now that it's geminal ones are coupling to each other as a doublet, and then they're also seeing the neighboring methyl group, which splits them into a quartet.
Exactly. So it occurred to me that I got a little bit ahead of myself. The reason that these 2 methylenes, and now I'll stop sharing my screen so that you can see my document camera if you pin that view. So of our salt, we could draw a plane of symmetry through the middle because this ethyl that's coming out of the page and the ethyl that's going into the page are equivalent to one another. However, when we take into account these 2 protons, if we were to exchange one of these 2 pairs with a deuterium and then draw the enantiomer or the mirror plane. Sorry, that's unnecessary. All that's necessary is to perform the thought experiment of exchanging one of these two methylenes with deuterium. If you swap the deuterium to be the other proton of the methylene, you'll find that they're diastereotopic. You end up with two different diastereomers, and diastereotopic protons are chemically inequivalent. So then the reason we see two signals is because, and it may be useful for me to make a pi-mole model at this point, but it would take a little bit for me to model it out. So maybe at the end, if someone still needs help visualizing this phenomenon, I can make a pi-mole model. Effectively, the two protons that are closer to the methyl group of the two methylenes, those, if you exchange them each with deuterium, you'll find those are enantiotopic, which means they're chemically equivalent. Those correspond to one of these two signals. And then the other two protons of each methylene that are enantiotopic with one another, but diastereotopic to the first set of protons, those will appear as the other multiplet. What Partho mentioned is the quartet is coming from the methyl group, which is expected. Each of these protons is split 3 times by this methyl group. But you additionally, because the methylene protons themselves are chemically inequivalent, they are diastereotopic, they split one another with a geminal coupling. And that's where the large coupling constant of 14.4 is coming from in our multiplet pattern. So they are in fact doublets of quartets each. 1 splitting coming from the geminal proton and 3 coming from the methyl group. I believe that is the whole question. So are there any follow-up questions about problem, this was midterm part 1, number 2.
I just want to clarify something you said. So the reason they look like sextets is because of the J coupling is a multiple of the other, right? Is that just, so it's just overlap that's making it look like a sextet, right?
It's just overlap. So if I were to exchange this large coupling constant for something that's not a multiple of another one, you would see resolved quartets. So this looks more similar to what we would think of as a doublet of quartet, but it just so happens that with a coupling constant of 4.4 and some line width, because we discussed earlier in class today how there's some width to each of these Lorentzian line shapes, it appears to be 6 peaks. In reality, it is 2 quartets that happen to be lining up on top of one another, which gives rise to this 1, 3, 4, 4, 3, 1 pattern.
Okay, so how close of a multiple does it have to be? Like you have 7.3 and 14.4.
I find it difficult to predict. I was walking through some of these problems both last night during the jam session and also on my own today. For some of the very small coupling constants, like 3 and 4 for the benzyl, the epoxide problem, sometimes even though they seem like they should be further apart, if you have enough line broadening, they can also seem coincident. So rather than being predictive, I would just use this tool to see if it appears the way that I think it might be. I can't think of a good predictive method to say how close is too close. James, do you have anything to say about that?
Yeah, I mean, one hertz or a little less than a hertz generally would be sort of the limits. So if it's less than a hertz or less than 0.8, it won't resolve. Now, in this case, the spectrum was run very, very concentrated, and the molecules are somewhat self-associated. So remember when I was talking about line width in class today, and I said normally your valleys go all the way down. So you look at that triplet at 1.39 ppm, 1.40 ppm, and it doesn't. Those lines are a little bit on the wide side. Had we run this spectrum at maybe a little higher dilution, we probably would have had less self-association. It was run super concentrated in chloroform, so it's a little broad. So these line widths are probably closer to 2 hertz. So you wouldn't resolve, with this particular spectrum, I wouldn't expect you to resolve even 1 hertz of difference. you probably would need close to 2 hertz or at least 1.5 to resolve it. But normally for a sharper spectrum, probably 1 hertz will resolve out.
Thank you.
Thanks, James. Any other follow-up questions about this past midterm problem? So the purpose of this problem was really to drive home the different types of diastereotypicity that you can observe in very specific systems. So again, if you need help visualizing this particular model, I'd be happy to build one in PyMol at the end of discussion. I've gotten a couple of people asking in the chat to go over problem number 4, which is nitrocyclohexanol. Okay. Is that, yep, that's this one. Okay. Proton NMR spectrum expansions are provided for 4-nitrocyclohexanol. Analyze the multiplets, determine the stereochemistry and preferred conformation, 400 megahertz. The alcohol appears as a broad singlet, so it's overlapping with our peak at 4.4 or 4.29. Methanol is at 3.39. Okay. So give the chemical shift multiplicity and coupling constants of the resonance associated with the CHNO2 group. So maybe the first question would be, how can we identify the CHNO2 group?
They're the most downfield protons?
Most downfield, it's adjacent to the, sorry?
They also tell us where the CH3NO.
Oh, great. Okay. I'd forgotten about that bit, but yes, it's adjacent to the most electron withdrawing group. So when the question is asking you to give chemical shift, multiplicity, coupling constants, it's helpful even just in structure determination to write these things down. So I'm just going to keep track on the right side of my screen if I can give myself a little more room. So for the peak at 4.4, what pattern do we observe and what are the J values? So that's this multiplet right here.
I got a triplet of triplet.
Okay, I agree with that. And what J values?
10.8, 4.1.
Okay, so that takes care of 1A. 1B, give the chemical shift multiplicity and coupling constants of the CH resonance associated with the one adjacent to the alcohol. It should be clear which one this is. It is the 3.76, I'll call that 3.8. And then what is the multiplicity of this multiplet?
Same one. Triplet, triplet.
Say again?
It's the same as the other one.
Also a triplet of triplets. And what are the J values for this
I
multiplet?
got 10 and 4.1. I think it's the same, almost the same.
Does it make sense that it would be almost the same? Or rather, let me rephrase that question. What is the fact that those two methine resonances looking similar to one another potentially tell you about the stereochemistry of the molecule?
They're in the same place.
What do you mean by that?
If you draw out a chair, they must both be either up or, well, they must be both up, I think. Yeah.
So you mean the proton should both be up.
Is it
So I agree with
trans isomer?
Right. So this would be the trans isomer of this particular molecule. So the options are axial, which would clearly ring flip to be trans, or we could have one group equatorial and one group axial. But what we've just identified is that the two methine signals, so each of the H groups that is on the same carbon as one of our two electron withdrawing groups, they appear very similar in that they have a large coupling and a small coupling on the order of 10 and on the order of 4. Based on what we know about cyclohexane systems, what are those two coupling constants associated with? What types of coupling?
Axial and axial equatorial.
Right. So if our methine has an axial-axial coupling, and if it happens to be a triplet, that strongly implies that both of these CH groups have to be axial, which would mean that our electron withdrawing groups have to be equatorial. So just by intuitively knowing that we have two axial-axial couplings, we've determined the stereochemistry of the cyclohexane. So now 1C is asking, what is the stereochemistry? Okay, so we figured that out, sorry. Annotate the diagram to reflect stereochemistry and conformation of the molecule. So I've been highlighting that. That would put our HB axial, HA axial, and each of our electron withdrawing groups trans. From the data on the preceding page in your answers to 1A and 1B, give the following coupling constants. So now might be a good time to annotate these other splitting systems. So this looks like 2.3, 2.1, 1.95, and 1.42. Does anyone have these coupling patterns annotated? So let's see, this would be 2.3. Based on what you know about the system, what is that signal? What is that multiple?
I put
beta to the next. Go for it.
No, go ahead. Sorry, I think I might have answered the wrong question.
Okay, I was gonna say, should that be the beta to the nitro group?
So so that's jumping ahead of where I was at. Why do you say that it's beta to the nitro group though? Because your explanation of why you determine that is also informative about what the multiplet pattern is.
Oh yeah, because I thought that the other one was, because this is more downfield, so just the effect of the more electron withdrawing.
Okay, I see what you're saying. Is it the equatorial or the axial proton that is beta to the nitro group?
That we get from the coupling constant, right?
Right, which is why it's useful to determine what type of splitting pattern this is.
So for splitting, it's DQ, doublet of quartet.
Okay, with what J values?
I didn't really look too closely, sorry, but I just know it's a DQ.
So if this is one of the methines, methylene proton beta to our nitro group, is it axial, is it equatorial? Can someone explain which coupling constant they looked at to determine that?
If it's axial, it would have one large coupling constant and one small one, but if it's equatorial, it would not have that large one, right?
What would the large coupling constant be?
In the ballpark of 10.8.
And which coupling constant, what type of coupling is that?
That's axial-axial.
Is there a larger coupling that we would expect for one of these beta protons, proton beta to the nitro group?
Yes, I think so. But I'm not sure for this one.
Are you talking about the HF to the HB coupling?
HF to HB. So we say again?
Geminal coupling.
Geminal coupling. Yeah. What is the ballpark Hertz coupling for geminal couplings?
Calling a friend. I don't remember off the top of my head, but I think it's 12 or greater. I think it's.
Sorry to cut you off.
No, both of those I would agree with. So in the ballpark of 14, maybe 12, depending on circumstances of conformation on the molecule. So in these coupling systems, do we see a large coupling constant that we would associate with the geminal coupling on the order of 14 Hertz? And if so, in which pattern? So I'm really quickly just going to summarize so that everyone is on the same page. So we've already identified the stereochemistry of the molecule, and we've identified HB is an axial proton adjacent to the nitro group. We identified that from its axial coupling to HF. Same for HA on the other side of the molecule. We're now trying to determine which of these signals is associated with all of the other protons in the system. And there's three types of coupling, or rather three sizes of J value that could be diagnostic in solving this molecule. One is the aforementioned axial-axial coupling between HB and HF, or between HA and HD, which is 10.8 or 10 hertz. One is an axial equatorial or equatorial coupling constant, which would be between HB and HE, or HA and HC, and that is on the order of 4.1 hertz. And then finally, the one that we haven't identified yet, but we know should exist, is between HF and HE, which is somewhere around 14, the Geminal coupling constant, the largest one that we would expect to observe. So if we are still trying to identify C, D, E, and F, and we have two downfield signals that are a bit clustered together, and then two more upfield signals, these to me look like they have larger J-value coupling constants, because overall these multiplets are more spread out, and we even have something dispersed. It looks like a quartet of something. I may be getting it wrong. It could be doublet of whatever. But with that information, can someone stake a claim as to which of these signals could have a geminal coupling? And if so, which?
Don't they all have geminal coupling, like the ones that are more upfield here, right? Because if one couples, then the other has to, right?
They do. Yes, you're absolutely correct. They do both have geminal coupling. And so because of that, maybe I should change my strategy, or change our strategy. How else can we identify these other protons based on information we already have? The information we already have being the J coupling constants of those multiplets.
I think we can, oh, sorry.
No, go ahead. Go ahead.
I was just gonna say, I think we could assume that the coupling, at least for I guess 4.4 ppm, TTJ 10.8 and 4.1, since we know what that is, we could assume that those coupling, the 10.8 and 4.1, are for nearby proton coupling. So assuming 10.8 would be axial to axial and 4.1 would be equatorial to equatorial, we could determine where it is, because we know that the 4.4 is located to the NO2, the nitrate, I believe. I'm not sure. And then we can do the same thing for the other one as well.
Exactly. Coupling is reciprocal. If HB is coupled to HF with either 10.8 or 10 hertz coupling, axial-axial, then that means in the multiplet for HF, we should observe that same coupling constant to HB. We've identified HB and HA already. HB is the one that's more downfield. HA is the one that's more upfield. The difference between the two is a very subtle difference in the Hertz coupling constant of the axial-axial, presumably because these are in two different chemical environments. One of these electron withdrawing groups is affecting it differently than the other one. And so fortunately for us, we can say that between HB to HF, that axial-axial interaction, or between HA to HD, axial-axial, one of them will have a coupling constant of 10.8. One will have a coupling constant of, just for clarity, I'll write 10.0. So now, in any of these unidentified multiplets, do we find an axial-axial coupling that is either 10.8 or 10.0? I see some nodding. Would someone like to share which one?
Is it?
It looks like, all right, my
Go
bad.
ahead.
Go ahead. Oh my goodness.
Yeah.
Okay, I'm gonna say it. The ones that are more upfield, if you look at like the second splitting after the first big one, then you got another like 10, I would say. So yeah, like we were kind of thinking earlier, the upfield ones have that axial coupling.
So if we were to identify the J values, maybe we won't call whatever the multiplet pattern is yet, but if we were just to identify the J values in, this is the multiplet you were discussing, right? 1.95 ppm?
Yeah.
So you picked out, was it 10.8 or 10.0?
Oh, I just kind of eyeballed it. I saw it was a two big couplings and a little one.
Mm-hmm.
And I said, that looks like the Geminal equatorial.
That's what I did also, Brian. I didn't actually go in and take those ppm data and convert them to hertz and then find the actual J values. But this is a good lesson. I suppose now we all know better, right?
I wouldn't say knowing better. Intuition is also useful. And what your intuition led you to was, and let me just clarify to make sure we're in agreement here, that these more spread out multiplets, these quartet-like multiplets, these contain the larger of the two axial couplings, and the two that are less spread out have the 10.0 hertz axial coupling. Is that correct?
No, I think it's that the two downfield peaks only have geminal. They have one geminal and two smaller axial equatorials. And then the upfield peaks, the in-name quartet peaks, contain two larger J couplings, one of them geminal, one of them axial, and then a smaller axial equatorial. And I think it sounds to me like most of us just kind of eyeballed that. It was like, oh, these are going to have one large and two small, and these are going to have two large and one small. A sign.
I see what you're saying now. So that means that the multiplets that did not have an axial coupling would have to be the equatorial peaks. They have one large geminal coupling. So HE would have one large geminal coupling to HF, and it would have one small equatorial coupling HE to HC, but it would not have and it would have the equatorial to axial coupling of HE to HD, but it would not have an axial interaction because it is an equatorial proton.
Exactly.
And so that means that you assigned HE based on its chemical shift, which is reasonable. HE is the more downfield of the two patterns that lacks an axial coupling. And that was, can you remind me again, did you assign that to the quartet looking one or the doublet or doublets looking one?
I chose E as the one at 2.35.
Okay. And I'm sure that we could go in and use the Hertz coupling constants to eventually assign what each of these, in fact, the question might ask that. Okay, the question does. All right. So thank you, Chris and Brian, for your help in identifying which signals correspond to which protons. Now we need to give each of the coupling constants. But before we do that, is everyone on the same page with how we assigned C, D, E, and F? Okay. If there are no follow-up questions, then JAC, well, are any of these the ones that we've already identified? Yes, they are. Okay. So starting with HA, we have two coupling constants, 10.8 and 4.1. One sec, I'm going to read the chat really quick. Oh, yeah, of course. Okay. Of the two coupling constants, HA, one is large, one is small. Which is which? Which protons is it coupling to?
He's coupling with the small one to HC and then the big one to HD.
Exactly. So HA to HD is an axial-axial interaction. We've already identified based on multiplet analysis that the large J value of HA is 10.8, which means that A to D, and we should also see this if we go back to the signal for HD, we should see a 10.8 coupling constant, but that means that we can assign this Hertz coupling value to be 10.8 Hertz. Using similar logic, B to F should be 10.0, which is here. So now,
I actually have those switched. My reasoning was HB and F will be further downfield because they're closer to a stronger electron withdrawing group. But again, that was just like generic reasoning and nothing rigorous. But
sorry, go ahead.
Maybe just in this moment, kind of a trivial detail because the values are close enough. But anyway, I have them switched.
I may have gotten tripped up and accidentally switched them during my explanation, but I think it's reasonable to say that if HA is the 10.8 coupling constant, then we would expect A to D to be 10.8, because when we looked at the multiplet pattern for HA, we identified that the large coupling constant was 10.8 Hertz.
Can I say something as well?
Yes.
I think Chris is totally correct. If you look at the very bottom NMR, I think we agreed that the leftmost or most downfield peaks were the 10.0 coupling constant peaks. So it's true that like the ones close to the nitro group are downfield, and those are the ones that have the large coupling constants. I don't know if that makes sense.
I don't know if the ones downfield have the 10. I thought we said those don't have 10.
10.8 is the most downfield one.
Oh, for real?
No, I don't think.
In that case, I don't know how it works.
Can I chime in here? So I never expected anybody to be able to analytically determine among the 2.08 and 2.32 ppm peaks which was associated with which, although I figured many people would infer it was the one more downfield associated with the nitro group. So mostly I was interested in associating those two peaks with either the axial or the equatorial hydrogens in the middle of the molecule, and then the two peaks at 1.43 and 1.95 with, again, either the equatorial or the axial ones. So I specifically didn't need or expect such a granular resolution. I don't know if that helps.
Okay, my mistake then. I was looking too deeply into it. But the logic of how we chose the difference between HF expecting to have an axial coupling and HE expecting the largest coupling constant to be geminal, but HE would not have an axial coupling, that logic still holds.
Absolutely.
So in that case, just really quickly, maybe someone could clarify, A to D should still be 10.8 and B to F should still be 10.0, correct? Okay. In that case, if we need
Wait, you said A, now I'm confused.
Oh no.
Now I'm confused. So A to D, was the less downfield of the two, right?
Agreed.
Oh, you know what? This is my bad because in my head, I assumed that A would have been the downfield peak, but A is the one that's adjacent to the alcohol, which is this signal. So if I just swap the order of these two, I'm sorry. Yes, that has been my mistake. So the signal A No, I shouldn't speak in terms of signals. We should say this is HB, which is next to the nitro group. This is HA, which is next to the alcohol. Therefore, HB has the 10.8 coupling constant. Is that right? Okay, cool. Okay, we're on the same page. In which case, B to F is 10.8. A to D is 10.0. My bad for having the two triplet of triplets swapped from the beginning.
Yeah, who labeled these protons?
I did. So this was my way of basically trying to provide a template for an answer so I could get inside everyone's head, but leaving it open-ended enough that I didn't indicate anything about the stereochemistry or the conformation of the molecule.
Wait, I got a little confused. Isn't the proton from the nitro group is more downfield?
Yes. So
Okay,
the proton adjacent to the nitro group is HB, which we assigned as the multiplet at 4.4.
Okay, and then the questions in the homework say 1A is from the nitro group. So does that mean that it should be 4.4 ppm?
Wait, HB, oh yeah, I just labeled that. Right, HB, so they are not written in any particular order. I just asked basically, I put on these letters and then I just asked people to go ahead and give the shifts associated with them. And I think I created some confusion because I probably should have labeled it in the opposite way. And then I think everyone would have been comfortable. Okay, A is the most downfield. And instead I made A the next to the most downfield. So I think I
got the
see.
right answer in the end, and that's what mattered. Are there any follow-up questions on problem? I think this was 4. So to just for completeness, identify the two resonances associated with HC and HE, and then HD and HF. This was the logic we used earlier, which is that E and C and E. Okay. Changing the size. C and E are our equatorial protons. F and D are our axial protons. The way that we identified them is that for F and D, we would expect to see axial-axial interactions. For E and C, we would not. And the only large coupling constant would be the geminal coupling constant to the adjacent proton. Okay, any last questions about 4?
I guess I have a couple of quick comments here. So yeah, so there were sort of 2 strategies on this last part that I think were useful. One was basically looking at those multiplets and saying, oh yeah, of the ones at 2.1 and 2.3, I kind of see one big coupling. It's sort of doublet-like with other splittings. And the ones at 1.9 and 1.4 are sort of quartet-like with additional splittings. In other words, there's 3 big couplings. That's one way, and say, okay, that means the ones on the left have just 2 geminal couplings and then a bunch of axial equatorial types of couplings, but no axial-axial couplings. The ones on the right have 3 big couplings, so there's a geminal coupling and 2 axial equatorial couplings. Now, the other thing that's really cool with any sort of multiplet, if you make your splitting tree, the distance between the outer 2 lines is the sum of all the J's. So if you have a triplet, the distance between the outer lines is 2 times the J value of the triplet because there's 2 splittings. If you have a triplet of triplets, the distance between the outer lines is 2 times the big J plus 2 times the small j. It's the sum of all of the j's that make it up. So even if you can't recognize that the peaks at 1.9 and 1.4 look kind of like quartets, and the peaks at 2.1 and 2.3 look kind of like doublets with a bunch of other couplings, you can recognize, oh, wait a second, those peaks at 1.4 and 1.9 are wider. They span a bigger range. They span well over 1/10 of a ppm, well over 40 hertz. For those, the sum of those coupling constants is more than 40 hertz. The sum of those coupling constants, right? One of them runs from 1770 to 1741 just on the lines picked. Is that right? Oh, wait, no, that's the front. Never mind. But it's more than 1/10 of a ppm. It's more than 40 hertz. The other one is much narrower. It's less than 1/10 of a ppm. And so you start to think, wait a second, those wide ones, we've got like 2 10 hertz couplings in there and maybe a 12 or a 14 and maybe another 3 hertz for good measure. That brings us up over, over 40 hertz. But the other one has a geminal coupling, maybe it's 12, maybe it's 14, and then a bunch of axial equatorial couplings. That thing never gets wider than about 20 hertz. It's about half as wide as the other one. So no matter how you slice it, whether you can recognize the patterns or you can just say, I'd expect this one to be wider than that one, you can go ahead and figure out that the ones on the right are associated with the axial hydrogens and the ones on the left are associated with the equatorial hydrogens.
Thanks, James. Okay, the next person in my chat asked for exercise 6.4, which I believe was one of the Silverstein problems. So if someone could help me find the page in the PDF for that one if I don't find it first. Oh, but I did find it first. Okay, 6.4. This has fluorine coupling. So the theme of all the Silverstein problems from this particular problem set were heteronuclear couplings to protons. Would someone like to walk us through their thought process, starting from the mass spec and continuing through all the spectra?
I think we got a CF3 group because you got a molecular ion minus 69 mass units. And when I was looking for fluorine stuff, that was I don't know. I think that's right. That one helped.
So which peak transition is the loss of the, so sorry, you said a CF3 group?
Yeah, at 175.
Got it. Okay, so 244 to 175 would be loss of CF3. And what does that say about the overall molecular formula of the molecule? Or is this given? Is this one of the ones where the molecular formula is given? No, it's not.
That's as far as I got on this one. So.
Okay.
It does tell us that we have CF3s. I don't know if you knew that, but it did tell us that.
Was that from the beginning of the problem set?
Yeah.
Yeah, there should be 2 CF3 groups.
So that's helpful because it gives us 6 of the atoms. So then what amount of mass does that mean we're missing? And then can we glean any information about possible heteroatoms or numbers of protons from the proton NMR or the carbon NMR? Does anyone?
You have 3 unique methine groups and then 3 unique tertiary carbons or quaternary carbons.
Yes. And then let's just make sure. Okay, yeah. That's not involved with the multiplied at 77. Do I remember what that's corresponding to? Let me think for just a second. Right, 3 distinct quaternary carbons. Okay, yeah, we're on the same page now. Do we have a molecular formula yet?
So I think on the mass spectrum, 77, so I think we should have a molecule.
Sorry, Ming Hao, I couldn't hear you very well at all.
So I don't know if this is correct. It might not be correct. But is it C8, H6N2F6? That's the closest one I could get to a full number.
Closest to 244 as in it is 244 or it's a couple of mass units off?
Oh, it is 244.
Okay. Does anyone agree with that molecular formula? So if I remember correctly, you mentioned 2 nitrogens, which is consistent with the nitrogen rule. 2 nitrogens would give an even mass. Do we see any evidence for nitrogen containing functional groups in the IR or in the proton NMR? So if not a nitrogen containing compound, what other molecular formula could get us to the correct molecular mass?
I had a C9H6F6O.
That, I believe, is correct. Yes. So, first of all, how many degrees of unsaturation?
3.
3 or
4.
4.
Yes.
I also get 4, which is great sign for an aromatic benzene ring. 4 degrees of unsaturation would all be there. We see evidence for that in the proton NMR, so we have a benzene ring. What does that mean about our oxygen? What functional groups could the oxygen be if we've already used up all of our degrees of unsaturation?
Alcohol?
It could be an alcohol. Technically, it could also be an ether. Maybe I'll have to phone a friend for help with identifying the alcohol in this compound. James, is the reason that the IR for the alcohol isn't quite so intense because of all of the electron withdrawing groups adjacent to it?
I'll be darned on this one why it's not so intense. I am surprised. I do think it's interesting that we see what looks like a monomeric alcohol peak at 3,600, as well as a hydrogen bonded alcohol peak at 3,548. And so, often that's characteristic of a sterically hindered alcohol. But I'll be darned. I guess the question to me may not be why those alcohol peaks are so weak, but why the other peaks at 1,200 and so forth are so strong. And I think this harkens back a little bit to the polymer IR problem where one of the problems I gave was a fluorinated polymer. And I think the CF peaks were really strong in the IR. Various peaks associated with the carbon-fluorine single bonds. That's my best guess. Those bonds have a big dipole moment, right? Fluorine's the most electronegative element. I think carbon is, if I remember, 2.4, but fluorine is 4.0. So those bonds have a big dipole moment. So maybe the reason the alcohol peak is so weak is simply that relative to the carbon-fluorine stretches, It's just not as strong. It's way stronger than the aromatics, for example, and way stronger than those little, you can almost see that little phenyl pattern, that little out of plane pattern between 2000 and 1600 or thereabouts. So that's my best guess.
That seems reasonable. I didn't consider that one, and I do remember the fluoridated polymer problem. Those were strong CF stretches. So if we're using the fragment method, we've identified, based on just what was given to us, 2 CF3 groups. We have a monosubstituted benzene because we have integral of 5 protons, which means it can only be substituted at one of those carbons. And we have an alcohol. And based on our molecular formula, there's only one way that those fragments could come together. So I'll just tell you that it is I'm not sure what the naming of this one would be, but it's toluene with an alcohol and 2 CF3 groups on that exocyclic carbon atom. So that's our structure, but maybe it would be more interesting to, what would be the most useful thing to discuss? So I know that I'm curious because I have since forgotten why we get this interesting pattern in the...
Aren't those 3 big peaks that go off the chart, the solvent peak?
So the 3 large ones are associated with deuterated chloroform. This is the 1-to-1-to-1 triplet of deuterium splitting carbon-13. But what about the pattern that is coincident with it? And in thinking about it, I actually just remembered what this corresponds to. So
Septet, right? Septet from the carbon is saying 6-fluorine.
Yes.
Carbon that is...
And it makes sense that I would say that it makes sense that a CF3 group would be roughly coincident with a chloroform peak because 3 halogens, in this case, one is a methine for the chloroform peak, and one of them is a quaternary carbon in the case of the 2 CF3 groups. So that's this carbon that's being observed that is conveniently right in between our residual solvent signal.
And that carbon is the carbon that has the oxygen and the 2 CF3 groups attached to it, as well as the phenyl group, right?
Oh, you know what, James? Yeah, you are right. And I just remembered the even more interesting part of this problem. Thank you. Where does the carbon of the CF3 group show up? So I misspoke earlier. This signal is corresponding to the alcohol carbon, the one that has the 2 CF3 groups on it. Which of these carbon signals corresponds to the carbon of the CF3 groups with 3 fluorines on it?
Signal 5. Or, okay, so if we look at 1, 2, 3, 4, if we look at that peak at around maybe 124.5-ish, it actually looks kind of like a quartet. So the ones at like 124.5, yeah, 120, 120.8, and then 117 and 128.5-ish. That's just like a really big quartet.
Does anyone have their notes handy? What is the J coupling constant in Hertz of a 1-bond carbon-13 to fluorine-19 coupling?
Okay, this might be wrong. Like either 44 to 81 or 3 to 25.
So those are CH couplings.
Oh, my bad.
So that last, you've got some nice ones. In the last table on my handout, it's table 4.3, gives you some CF couplings. I don't know if anyone has has that handout handy. Pretch gives you couplings out the wazoo for this, but Silverstein gives a nice typical one bond CF coupling in this rather cryptic table.
So I believe I have the correct table in front of my camera now.
Yeah. So what do we see for a typical one bond coupling for a CF coupling? Anyone want to read it for me?
$271.
Yeah, really, really big. And how far on a 75 megahertz carbon NMR spectrum, how far apart in ppm would two lines be that are separated by 200 ppm, 200 hertz and change?
Roughly 3 or?
Roughly 3, yeah. And that's what you see in this quartet. And it's so easy to miss those outer lines of the quartet. And whoever made this problem for Silverstein must have really worked hard to get all 7 lines of the septet of that quatcarbon, because all the 7 lines there, it's so easy to miss those outer lines amidst the noise. And on the quartet, it's so easy to miss the outer lines of the quartet among the noise, noise impurities, particularly, and probably impurities, particularly the one at 128.4 or thereabouts, where you can kind of sort of see a little bit of something going on with that. That's probably a chemical impurity right over there. Hard to tell. It could just be noise, could be a chemical impurity. Clearly, there's a couple of little other things in this spectrum.
So thank you very much to everyone who reminded me that my own understanding of this problem was incomplete, because I don't frequently look at fluorine coupling, but now that we're all on the same page, it's after 6 p.m. Anyone who would like to is more than welcome to peace out. The rest of the session is being recorded, and if something comes up, you can watch it at a later time. There are more questions in the chat that I'm going to try to get to. So problem 812, I guess is back up here. Yeah, 812. So let me, sorry, I need to sort through all my own paperwork. Okay, so molecular formula for 812. Since we're going after hours, maybe we can take a bit of a quicker pace.
I got C8H7OF.
C8H7OF. I agree. How many degrees of unsaturation is that?
5.
Okay. We see evidence of an aromatic region. How many times is that benzene ring substituted?
Twice.
And you can tell from the 4 protons. Where is our last degree of unsaturation coming from?
Ketone?
What kind of ketone? Is it stronger than your average ketone or weaker than your average ketone?
Weaker.
Yes. And what could contribute to that? Oh, there he goes.
The benzene ring?
Yeah. So this suggests that actually this is an interesting point. If the fluorine was on the carbonyl carbon, would we expect that carbonyl to be stronger or weaker? What do we know about acid halides, those carbonyl stretches?
They are strong.
They're stronger because of this interesting charge separation effect. So this tells us that our ketone is probably on the phenyl ring rather than an acid fluoride. And then I suppose the more obvious data pointing to that fact is that we see a very, very characteristic alpha or methyl group alpha to a carbonyl. It's a methyl singlet at 2.5 ppm. And we only have one atom left. All that remains is to choose where it goes on the aromatic ring. So our two fragments so far are benzene ring. It has an acetyl group on it. So where is the fluorine relative to the acetyl group? It can only be ortho, meta, or para.
I want to say it's para.
Why do you say that?
Because I'm looking at it, and I think for para it would have like the HA prime, HB prime version, and then when you look at the peaks around 7-ish and 8-ish, you can see that. Well, I'm assuming they're also coupling with the fluorine, so there's the distance, the coupling for the triplet is like around 9-ish, and then for the doublet of doublet, I put 6 and 9. So I think one of them has to be ortho to fluorine, and they all have to be ortho and meta, or has some ortho and a meta coupling.
So
from there, I'll let someone else explain. I think I ran out of thoughts.
What is the Hertz coupling constant of an aromatic fluorine to the other protons on the aromatic ring? This was also in the appendix we were just looking at, just in a different spot.
It's around 5.5 to 6 for, I believe it's meta, and 9 for ortho.
So let me make sure I'm getting the right part. Yeah. So 6 to 10 hertz for the ortho coupling, 5 to 6 hertz for the meta coupling, and sometimes you see 2 for the para coupling. And what you might notice is that that's actually kind of close to the regular proton-proton ortho, meta, and para coupling that we see. It's not exactly, but it's on the same order. And I think something perceptive that Tran pointed out is in a para-substituted system, you would expect to see non-first order coupling or remains of non-first order coupling. And that's the explanation I would use as to why. Am I sharing the right screen? Is everyone seeing my PDF? Okay, sorry, I thought I clicked the wrong thing. Why we're seeing quite a bit of, I don't know, fuzz around what would otherwise be a well-resolved doublet of doublets and a well-resolved triplet. So in that case, which of these signals is ortho to the fluorine and which is para to the fluorine? Anyone can answer.
I don't know, but I put that the more downfield one was meta to the fluorine and the more upfield one was ortho to the fluorine.
That's also my logic, just based on the electron withdrawing effect of the acetyl group, because you can draw a resonance structure that puts a positive charge at that position. In addition to that, the protons that are ortho to a proton and ortho to a fluorine, because those coupling constants are similar to one another, it's 2 large J's, so you observe a triplet. For the proton that is ortho to a proton but meta to a fluorine, you observe 1 large J from the ortho proton coupling and 1 small J from the meta fluorine coupling.
And one thing that's cool about meta coupling to fluorine is it's way bigger than meta coupling to a proton. So normally that's for a proton, that would be like 2 hertz for a meta coupling, 1 to 3 hertz. And it's about 5 hertz for a meta coupling to a fluorine, which is very cool. So you look at that, and that's like a doublet of doublets with like 8 hertz or 7 hertz for the big coupling and like 5 hertz for the small coupling, which is very different than what you'd see for, metacoupling on a hydrogen, which just sort of counterintuitive.
And the last thing I'd like to point out is based on our understanding of fluorine coupling is reciprocal. We would expect to see a triplet of triplets for the fluorine because the fluorine is being split by 2 orthoprotons and 2 metaprotons, and that's exactly what we observe. So, I am actually running low on time right now. I have things that I need to attend to before 7 p.m. and I don't want to throw it on to James, but if you have remaining questions that neither of us have the time to answer and you would like them answered before you turn in this problem set, that's totally fine. You can email them to me and I'll be in lab. I'll be checking my email. But James, is it all right if I leave this meeting and you?
I can hang out here for a little bit longer. I'll take any questions. I may need to answer the doorbell at some point because Mike wants to come by and return my computer to me that he borrowed. But that'll be fine. I'll hang out for a little bit.
Okay. Then in that event, good night, everyone. And remember, if you have a question about turning in the homework after emailing me, just wait. It's totally fine. And someone had a question about I'll just answer this privately really quick and then I'll head. Just making sure confirmed receipt. All right. Have a good night, everyone.
Thank you. Professor, I have one question that I promised James I wouldn't ask in the official discussion. And the question is, in problem 1 that we had to do was proton NMR for an amino acid. The question is it some exotic synthetic amino acid or is it a naturally occurring amino acid? And
it is not one of the proteinogenic amino acids.
That's good to know because I spent a bunch of time yesterday and today trying to go through all of them and be like, well, that won't work and that doesn't work and this doesn't. So good to know. Thank you.
So let's see. Trying to remember, I don't think I make a problem out of this later. Maybe I do, but yeah. This is, although it is not one of the proteinogenic amino acids, you have tons of it in your body and on your body. And I will leave it at that mystery because there are plenty of non-coded amino acids that we have lots of.
All right. Thank you for the hint. I'll do some more homework and then try to report back.
I think later on, if I remember correctly, I believe this one, okay. This one comes back and it's, to be honest, the problem is a little bit of a dog. So it's going to come back in the NOE problem set. And the reason I guess I'm not being more forthright in giving you an answer on this is we're going to go ahead later on and it's either next problem, it's once we introduce the nuclear Overhauser effect. So it's probably 2 problem sets hence. We're going to come back and try to determine the stereochemistry of this molecule. And it's a bit of a dog because the answer that you get, I'd say it's practically random what people will get on this. And we're going to talk about it, which is fine. because I hate to say, everything isn't black and white. And there really is a stereochemistry, and we're going to talk about why it's so complicated. So at that point, you will get the structure of the molecule. If you're dying of curiosity and you want to think about my riddle, you can think about it and you will probably figure it out.
I am dying of that curiosity, so I will think about it over dinner right now and spend some time this evening and the next few days trying to riddle it out. So thank you for the hints.
So it's interesting. Organic Syntheses is a compendium of what started. Are you familiar with the series Organic Syntheses published by the ACS? And it's a series of synthetic procedures, and each year they publish a new volume. Nowadays, the volumes highlight the best sort of synthetic methods, new synthetic methods, and the procedures are done really well and they're checked. But these things go back, I think, to about the 1940s, I want to say. It may even be 1930s or 20s. We must be up in the 80s, and it's a volume a year. Yeah, so it's probably back, probably about 1940s that it goes back to. And back then you couldn't buy, a zillion different chemicals. So it started with procedures for making really simple stuff. And some of the procedures they make involve one of the procedures, I think, is for making some amino acids. And it starts with like 2 pounds of hair. So you go to a barber shop and you basically get the sweepings from the floor. And then you hydrolyze it, and then you take it through some crystallization procedures to get one of the amino acids. I don't remember which one it is. It may be cysteine that they get. Anyway, it is a very, very interesting procedure because they're basically just isolating it from an obvious natural product.
Which is cool. You have to applaud the resourcefulness of, we've got this abundant waste product, let's feed it in.
And that's probably where a lot of the amino acids are, obtained from these days, just from basically fractionating various proteins, hydrolyzing and fractionating various proteins.
Right. Cool. Thank you.
You're welcome.
See you all Friday.